Hi folks, we are on the Unit 2 Day 4 lesson, and this is going to be a continuation of what we did in the Day 3 lesson with dot product, but now we're going to look at the dot product using our algebraic vectors instead of the geometric. So we're going to need to come up with a new formula because the formula we have depends on us knowing the magnitudes of our two vectors and also the angle between them, which we almost never know when we have algebraic vectors, but the dot product is actually going to become a really convenient way of finding the angle between two vectors for our algebraic vectors. So we're going to take a look at the formula we had yesterday. We know, and this is the formula for dot product. We're just going to combine together some other kind of prior information. So with geometric vectors, we know that this dot product is the magnitude of A times the magnitude of B times the cosine of the angle between them. And remember that that gave us a measurement of how well those vectors were working together. It's basically the magnitude of one vector times the amount of the second vector that's in the same direction as the first. So it's like the component of the second vector that's working along with the direction of the first vector. So we want to get something that will work for this, but is in terms of our algebraic vectors like A and B down here. So what we're going to need to do is use some other information that we know about kind of general math and trig stuff and change this equation into something that we can use just our component forms of our algebraic vectors to find the dot product. And it gets a little bit messy, but we do end up coming up with a really nice formula. So the main thing that I look at is, what do you know that has a magnitude and a magnitude times the cosine of the angle between them? To me, that looks like the end of the cosine law. So we're actually going to use the cosine law to derive a new formula based on this. It's from the same formula, but to be able to find this formula that we can use for our component vectors for algebraic form. So first of all, we're going to define our two vectors here, A and B, and I'm just going to draw those out. Any two vectors there, A and B, and we've got this angle theta in between. So we know that the cosine law would be written to find this side if we were using that cos theta. So remember that vector A goes from the origin to a point A that has this coordinate. And then vector B goes from the origin. Remember, vectors don't actually have a location, but in component form, they're written as if they started from the origin and went to another point, A or B. So this third piece of the triangle, I'm going to draw in as vector AB. And remember that vector AB, we get the components of this vector by doing the end point minus the start point. So the second x minus the first x, the second y minus the first y. So I'm going to use that. So the x component would be b1 minus a1 of this blue vector. The y component is b2 minus a2. You would subtract the y values of those. And then the z component is c2 minus, B3, there's no C's, minus A3. Don't know where I came up with C's. Sometimes we say A, B, and C. So here's my components of vector AB. Now I know that the cosine law will work for this triangle, and the cosine law would state that the magnitude of AB squared would equal the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times the magnitude of vector A times the magnitude of vector B times cos theta. And this is the part that looks really familiar because we know that from our geometric vectors, we know vector A dot B is the magnitude of A times the magnitude of B times cos theta. So this piece here is actually A dot B, and I'm going to replace that in the next step. So just to kind of write this out, I'm going to keep it all nice and the same. We could skip steps here, but just to make it real clear what's happening, magnitude of B squared minus 2, and then this is vector A dot B. So what I want to do now is solve for A dot B by substituting in these magnitudes. And it is going to get pretty messy, but it's manageable. We can totally do this. The magnitude of AB squared. Remember, the magnitude of a vector is the square root of the x component squared, the y component squared, and the z component squared. So this magnitude of AB is going to be the square root of B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. That's the big square root. But then this cosine law has magnitude squared. So that is such good news, because this squared out here will get rid of my square root in the magnitude equation. Same thing's going to happen, but a little bit less messy for those. So I will have the magnitude of A squared. So this is going to be the square root of A1 squared plus A2 squared plus A3 squared. And that whole square root is squared, which will cancel each other out. I'm just going to kind of, we will end up squishing in a little bit here. And then the square root of B1 squared plus B2 squared plus B3 squared minus 2A dot B. So again, this is kind of following down onto that line just because I'm out of space, but we really want to solve for that A dot B. So big deep breath. We can cancel out the squared and the square roots on each of those. I am going to have to FOIL out all of those, and I am going to kind of skip over a little bit of this work. So we get over here B1 squared minus 2A1B1 plus A1 squared plus, and then again kind of the same thing, B2 squared minus 2A2B2 plus A2 squared plus B3 squared minus 2A3B3 plus A3 squared equals, and this does get a little tight in here, so we get A1 squared plus A2 squared plus A3 squared plus B1 squared plus B2 squared plus B3 squared minus 2A dot B. And I'm kind of scooting that down. So hopefully you see that despite this really big amount of mess, I have a B1 squared, a B2 squared, and a B3 squared over there that will cancel out with those guys. And then I have an A1 squared, A2 squared, and A3 squared that will cancel out with those three. And then this ends up much, much nicer whoops, wrong color. So I get negative 2a1b1 minus 2a2b2 minus 2a3b3 equals negative 2a dot b. And then just dividing out each term by a negative 2, I'm just going to swap the order here. A dot b equals a1b1 plus a2b2 plus a3b3, which ends up as a pretty nice, neat equation. This is just multiply the x components, multiply the y components, multiply the z components. And that is going to be how we calculate the dot product in algebraic vectors. So it really is just taking the cosine law, making a big mess, foiling stuff out, canceling things out, using our magnitude formulas, and the fact that this end bit of the cosine law actually is the formula for dot product that we got from geometric vectors, it pops right out there. So it's not any kind of advanced math that you need to do this, it's just a little bit messy on the way. So this just kind of summarizes it works for R2 and R3. Obviously for R2 you just wouldn't have the Z components, it would just be A1B1 plus A2B2. But I don't have that written out separately because so often we will be working in R3. So for algebraic vectors, component form here, we just multiply the two x values and multiply the two y values, multiply the two z values, and add them all up. And that's how we're going to get dot product. You can write this, obviously the component form, we've written these all in component form, but if you had your vectors written in unit vector form for your algebraic vectors, that's going to work exactly the same way. We usually do see component form, but you would just instead take the coefficients of the i's, multiply those together, coefficients of the j's, multiply those, and the coefficients of the k hats, and multiply those. So first example here, we are given two vectors in R2, and we want to determine u dot v. So we see u and v. We just have to, again, careful with the notation, make sure you're showing a dot there. It is different than scalar multiplication. It's different than cross product that we're going to get to later in the unit. And you have to show it differently. So here I just multiply the x values and multiply the y values and add those up. So I get negative 6 plus 15, which is 9. So u dot v equals 9. Okay. So that's a pretty easy operation to do. Finding the dot product, it's not too tricky at all. The important thing, this is the number one, probably the number one use for now that you guys will have for the dot product. So this is like the very important, I maybe won't say most important. So this is a very important use of the dot product. We know that u dot v equals the magnitude of u times the magnitude of v times cos theta. Now we found on the previous step, because in part A, these are the same vectors, we found out that u dot v equaled 9. So we know that that's 9. We can find the magnitude of u just using the magnitude formula and the magnitude of v, and then we can solve for cos theta. So I'm going to say 9 equals, the magnitude of u is the square root of 6 squared plus negative 5 squared, and the magnitude of v is the square root of negative 1 squared plus negative 3 squared times cos theta. So 9 equals 36 plus 25, and then square root. I'm actually not going to, I don't want to make too much of a mess here, but I'm going to need my calculator to figure out cosine. So we've got here root, I'll do these separate, root 61 and then root 10 cos theta. So I need to solve this for theta to get my angle. So that'll be inverse cos of 9 over, this would be root 610, but if you put it separate, that's fine too. So inverse cos, I end up with an angle of 68.63 degrees. So this is the really important piece here, that now at the beginning of this lesson I said we don't often know the angle between two algebraic vectors, but now we can very easily find it out. If we have those in component form, we can find their magnitudes, we can find their dot product. The only thing left to solve for is the angle. Now, some people who are way better at memorizing formulas than me, some people prefer to memorize this. I feel like that's kind of silly, probably because I have a terrible memory for formulas. Some people kind of prefer to memorize that as its own separate equation. I always just kind of sub into the original formula and isolate, but it doesn't matter either way. So the next example is very similar, but it doesn't kind of break it down into steps like the first one. Sometimes they'll ask you for the dot product first and then ask for the angle between, but more often you will see just find the angle between two vectors, and you need to know that that's going to be a dot product question. So I'm going to start with u dot v is the magnitude of u times the magnitude of v times cos theta. And then I'm just going to do all those calculations right in this equation. So u dot v, I take the x components and multiply them, the y components and the z components, and add them all up. So I've got negative 3 times 5 plus 1 times negative 4 plus 2 times negative 1. So that's the dot product on the left-hand side. And then I have the square root of negative 3 squared plus 1 squared plus 2 squared, x squared, y squared, z squared in the square root. And then the square root of 5 squared plus negative 4 squared plus negative 1 squared times cos theta. So it gets a little bit kind of clunky and messy, I guess, but not too bad. So there I've got negative 15, all negatives, negative 15, negative 19, negative 21 over here. And then that's square root 9, 10, 14. And 5 squared plus is 25 plus 16 is 41 plus 1 is 42 cos theta. And then I'm going to solve for theta. So I'd have to divide these guys down and do second function cos. And so I get 150 degrees. Right on, actually. Remember that if if the cosine, or if the angle is bigger than 180, the dot product will be negative. So seeing that dot product as a negative value, I knew for sure that, that this would be an obtuse angle between 90 and 180. The last piece, oh, maybe I have 2 more examples. This is another kind of flashback from yesterday. When you see perpendicular, I want you to think the very first thing. So this says, find a value for t that would make vectors a and b perpendicular. The minute you see a perpendicular vector, I want you to think dot product equals 0. That's the most important connection in dot product that you can make. If you see the word perpendicular, your first thought should be dot product is 0. So we can just go right from there, and we know the fact that a dot b would equal 0, then we just do the dot product using the the components of the 2 vectors. So -1 times 2 plus 5 times -1 plus 7 times t equals 0. And then it's a pretty straightforward little equation. So -2 minus 5 plus 7t equals 0. 7t equals 7, so t equals 1. So pretty straightforward. The trick here is if you see the word perpendicular, you have to immediately think that means the dot product's 0. Something is going to almost always, probably 80 or 90% of the time, if you have perpendicular vectors, you're going to have to write down a dot b equals 0 in some part of your solution. The last question here is a little bit of a review from the previous unit, thinking about collinear vectors. Remember, we've got 3 points. Are these points collinear? If you see the word collinear, I want you to think scalar multiples. But, and I think you guys probably look at these and think, well, those are obviously not scalar multiples. These are not vectors. Sometimes because the vector notation and points look actually really similar, right? These are points, not vectors. You need to find vectors. So we need to figure out 2 vectors between these 3 points, and it doesn't really matter which ones you choose. You could pick AB and BC. You could pick AC and BC, AB and AC. It doesn't really matter. I'll probably do AB and BC. So vector AB, remember we do the end minus the start. So I have -3 minus 5. The x component of AB is -8 because it goes from an x value of 5 to an x value of -3, so it's moving 8 in the negative direction. And then 4 minus -1. Careful here with the minus and negative. I know it's a silly thing to point out this many times, but people really do make mistakes on that. So 4 minus -1 is +5. Okay, and then just keep myself color-coded here. Going from B to C, here I've got 13, because I'm ending at C, 13 minus -3, which is 16, and -6 minus 4, which is -10. So I think that that's pretty obviously a scalar multiple. Since BC equals -2 times AB, the points are collinear. Okay, it has to be x and y and z if you had it, if it was R3, that were all scalar multiples, the same scalar multiples for collinearity. And that is it for Unit 2, Day 4.